In this video, we are going to talk about vector spaces, and I think this is really exciting because I feel like this is where linear algebra really starts, and really it's a very fascinating topic with many applications. It's hard to even understand how many there are. But we'll get started first by defining what a vector space is, and essentially it's a set with two operations, which is an addition operation and a scalar multiplication operation. We'll talk about examples of vector spaces. Our main example is the vector space Rn, but we'll talk about other vector spaces, and then we'll talk about subspaces. So in this video, we are going to define a vector space, and this is actually quite exciting for a couple of reasons. One, which is this is really getting to the heart of linear algebra, and the other one is just the number of applications there are. It's really quite amazing, and we'll discuss that a little bit later. But what a vector space is a set of elements, V, and those elements are called vectors. We're going to call them vectors. And it's over some scalars. And then we have an addition operation, which is defined between two elements of V. In other words, an addition operation, which is defined on two vectors. And we have a scalar multiplication operation defined between elements of S, that's the scalars, and a vector. Moreover, if U, V, and W are vectors in V, and I'll try to remember to bold my variables if they represent vectors, and if A and B are any two scalars, by scalars we just mean real numbers, then these 10 properties must hold. So again, a vector space is a set of elements, a set of vectors, along with an addition operation and a scalar multiplication operation, and that basically follow or respect these properties. First is the closure in closure properties. First is addition of two vectors is closed. That means, and by closed, what that means is U plus V is still a vector in the vector space or in the set V. And the scalar multiplication is also closed. So A times V is still a vector in the set V. We'll give you some examples of when things are closed and when they're not, and this will become more clear. There are properties of addition that follow the commutative law. So U plus V equals V plus U. And again, you cannot take commutativity for granted, like we saw that matrix addition is commutative, but like matrix multiplication is not. So that would be an example of an operation that is not commutative. But if it's in a vector space, the addition must be commutative and also must be associative. So U plus VW has to equal U plus V plus W. There's an additive identity. In other words, there's a zero vector, and I have this in bold, in V, such that any vector V plus the zero vector always gives you back V for all V in your set. There's an additive inverse. So for every vector in your set, there's an additive inverse, which we'll denote with negative V, such that the vector V plus its inverse is equal to the zero vector. And then these are the properties the scalar multiplication follow. First, there's kind of this associative kind of property, but A and B here are scalars, V is a vector. So A times B times V is equal to AB times V. And A times U plus V, where U and V are vectors, is equal to AU plus AV. And then A plus B, these are two scalars, times a vector V is equal to AV plus BV. That's kind of these two, M2 and M3, are sort of distribution kind of things. And then we also have 1 times V is equal to V. So there's a unity, a multiplicative unity. And I wanted to make some comments on closures. So closures involve sets, and they involve an operator. So let's say our set is a set of integers, and V1 and V2 are integers. They're in our set V. So V1 plus V2 is still an integer. When you add two integers, you get an integer. So the set of integers is closed under the addition operation. Again, so you talk about sets being closed under an operation. Whereas V1 divided by V2 is not necessarily an integer, so the set of integers is not closed under division. Now that we have the definition of a vector space, we are going to look at three examples. The first one is the space of Rn. We will look in particular at R3. Then we'll look at the set of all 2 by 3 matrices with real entries, and let P2 denote the set of all real polynomials of degree 2 or less. Then P2 is also a vector space. So we will look at these 3, and we will show that they are vector spaces. So to show they are vector spaces, we have our sets, we have our operations defined, our normal addition of vectors, normal addition of matrices, and normal addition of polynomials, and scalar multiplication, also the normal ones. Then we will show that those addition and scalar multiplications, that these 10 properties hold. As I said, our first example is going to be the space Rn. And so in particular, I'm going to show R3 is a vector space. And then 2 example vectors that I have is the vector U, which is composed of the U1, U2, U3 vector, and V, which has components V1, V2, and V3. I need to show that these 10 properties, which I kind of rearranged so that I could have space down here, the closure properties, the properties of addition, and properties of scalar multiplication hold for our vector space R3. And we will start with C1, that is, the addition of 2 vectors is closed. So in particular, I'm just going to take my representative vector U and my representative vector V and add them together. And then by definition of vector addition, that gives me U1 plus V1, U2 plus V2, U3 plus V3, and the resulting vector is still a vector in R3. Therefore, addition is closed in R3. Next, I will look at closure of scalar multiplication. So when I have a scalar times a vector, I want to show we still have a vector in V. So I'm going to take my scalar alpha, just because my A's and my U's, they all look the same. So I'm going to make alpha my scalar. So alpha V is equal to alpha V1, alpha V2, and alpha V3. This is just simply by the definition of scalar multiplication of a vector. And so this is still a vector in R3. So I can say that R3 is closed under scalar multiplication. Next, I have my properties of addition, and they take up a little more space. First, I want to show that it's commutative, so that U plus V is equal to V plus U. So I have my 2 representative vectors, and I am going to add them together. And by matrix addition, I get U1 plus V1, U2 plus V2, U3 plus V3. And because now U1 and V1 and U2 and V2 and U3 and V3 are just real numbers, by properties of addition of real numbers, addition of real numbers is commutative, so I can make this equal to V1 plus U1, V1 plus U2, V3 plus U3, and then this is exactly the definition of V1, V2, V3 plus U1, U2, U3, which is equal to V plus U. Next, I will need to show that the addition is associative. So if I have U plus V plus W, that's going to equal to U plus V plus W. So I have U plus V plus W, and I'm going to do that addition first. So I have U, and I have V and W, so I'll add V and W first. And then to add these 2 together, by definition of vector addition, that's just U1 plus V1 plus W1, U2 plus V2 plus W2, etc. And now because these are just real numbers, I can separate these out, or actually I don't even have to rearrange them. So I can just separate this out to U1 plus V1, U2 plus V2, U3 plus V3 plus W1, W2, W3, right? Because these 2 are equal by the rules of vector addition. And now I have U plus V grouped together plus W. So that's the associative. Now I need to show there's an additive identity. I need to show a 0 vector such that V plus the 0 vector is equal to V. So my 0 vector in R3 is the vector 0, 0, 0. So when I add V to my 0 vector, I get V1 plus 0, V2 plus 0, V3 plus 0, but that's just equal to V. So I've shown that R3 does have a 0 vector. Next, I need to show every vector V has an additive inverse such that when I add V to its inverse, I get 0. So if someone gives me a vector V equal to V1, V2, V3, my additive inverse then is going to equal to negative V1, negative V2, and negative V3. So when I add V1 plus V2, I get my V1 minus V1, V2 minus V2, V3 minus V3, which gives me 0, 0, 0, which is my additive identity. The next properties deal with scalar multiplication. So first I have to show that I can group multiply by a scalar times v and then later multiply by another scalar, or I can multiply my two scalars first and then multiply by v. So that's what I've done here. I have ba times bv. So here I have b and v, and I multiply my scalar b times v. And then I multiply by a, and by definition I just multiply by a. And then this is also equal to if I pull out ab. So I have my M1 property done. I have these distribution properties. So the first one is a scalar times the sum of two vectors. So I have my scalar. I'm going to sum my two vectors together, and then I multiply by my scalar. Since I'm multiplying a times the first coordinate, a times the second coordinate, a times the third coordinate, I can also just distribute just because these are now just real numbers. So I have AU1 plus AV1, AU2 plus AV2, AU3 plus AV3, but now by the definition of vector addition, I can break these apart. So I can have AU1, AU2, AU3, and AV1, AV2, AV3, and that's just A times U and A times V. Okay, so that's my multiplicative kind of this distribution. Now we have another distribution law where we add the two scalars and then multiply by the vector. So here I have my two scalars multiplied by a vector. So my scalar goes in. Now these three are just real numbers. The a, the b, the v1 are just real numbers. So I can use my normal distribution law of real numbers, my distributive law of real numbers. And then from there, I can break these apart to two vectors, and I get av plus bv. And last, I just need to show that 1 times v is equal to v. So 1, the scalar 1, times my vector v is just equal to 1 times each component, which is just v1, v2, v3, which is equal to v. So we have just shown that R3, along with the regular definition of vector addition and regular definition of vector multiplication, vector scalar multiplication, I should say, that these two operations with this set of vectors satisfies all these 10 properties, then R3 is a vector space. And Rn, in this case we just did R3, but Rn is those are our prime examples of vector spaces. Another example of a vector space is the 2x3 matrices with real entries. So I wrote two representative matrices, 2x3 matrices, A and B. And now to show that the set of all 2x3 matrices are a vector space along with the regular matrix addition and scalar multiplication, I need to show that these 10 properties hold. And we will start with closure of addition. So if we have our vector or our matrix, our 2x3 matrix A plus our 2x3 matrix B, then we get this 2x3 matrix A plus B. So since it's still a 2x3 matrix, then matrix addition is closed. For C2, if we have a scalar, A times a matrix B, by the definition of scalar multiplication, we have this matrix here, which is still a 2x3 matrix, so scalar multiplication is also closed. To go through the properties of addition, first I have to show that addition of two vectors is commutative. So here I have A plus B, so I have written out my matrix A plus matrix B, and by definition of addition of two matrices, I have this matrix here where I have the component by component addition. And then because A11 and B11 are both real numbers and addition of real numbers commute, I can make that equal to B11 plus A11. Similarly, for A12 plus B12 can be B21 plus A21, etc. So then what I have is the very definition of B plus A. So I have shown commutativity. So next we'll look at associativity. So I have A plus B plus C. So here I have B plus C grouped together, and then I have them added together, and I have A over here. So when I add all three together, now this is a real number plus this real number, I have my A11 plus B11 plus C11, etc. And now I can break apart my A11 from my C11 and my plus B matrix then gets broken apart from my C matrix, because that's exactly the definition of my matrix addition. And then this is equal to A plus B grouped together plus C. So I've shown my associativity. Now I need to show an additive identity. I need to show a zero vector in V such that V plus 0 is equal to V for all V. So my zero vector is just the 0, 0, 0, 0, 0, 0 matrix, so I can confirm when I add A to 0, I get back A. And last, for every vector V, I have to be able to show I can find an additive inverse, such that when I add the vector with its inverse, it equals 0. So for A, its additive inverse is going to be negative A11, negative A12, negative A13, etc. So when I add A plus its additive inverse, so here's A, here's its additive inverse, I have this matrix here, which just gives me back my additive identity. Last, I need to prove these properties of scalar multiplication. So first, my scalar A times scalar B times V. So here's my scalar A, my scalar B times my matrix A. So according to scalar multiplication, that just equals to B times the component, each of the components of the matrix A. And then I move in my A, multiplying everything out. And then I can also take out A and B. So what I have is AB times A. My second distributive law, when I add the two vectors and then multiply, so I have my my A plus B matrix looks like this from definition of matrix addition, times my scalar, so I can multiply everything times a scalar, but now my scalar and my A11 and my B11 are all real numbers, so I can use my regular distribution law. So I can distribute the scalar A inside, and then I can separate out my two matrices. So I get that equal to the scalar A times matrix A plus scalar A times matrix B. M3, another distributive law, but now I'm adding two scalars and multiplying by a vector. So here I have my two scalars multiplied by a vector. But now again, I have two scalars, and this is also a scalar. These are three real numbers, so I can use my normal distributive law over here, and I can distribute A11 and multiply by A and then multiply by B. And now I can separate out my A and my B vectors, so I have scalar A times vector A plus scalar B times vector A. Last, and I say vector because now we're saying these matrices are our elements or our vectors. So M4, so I need the one scalar times a vector is equal to a vector. So 1 times our matrix is just equal to our matrix. So now because this vector, this space of 2 by 3 matrices with the regular matrix addition and scalar multiplication, they follow, or all 10 properties hold. That means this is a vector space. So I did spend a lot of writing to prove that, but there are 10 properties to prove. My last example is P2, where P2 is a set of all real polynomials of degree 2 or less. So here are two representative vectors. So the first vector is A0 plus A1x plus A1x squared, and my next representative vector is B. And again, my coefficient could also be equal to 0, so that also gives me things where the degree is 1, and if these A1 and A2 are both 0, then I have degree is less as 0. But anyway, so I want to show that P2 is a vector space under normal polynomial addition and scalar multiplication of polynomials. We will start by showing the addition of two polynomials is still a polynomial. In other words, the addition of the two vectors is closed. So A plus B, when I add two polynomials, I get back a polynomial. And if the two polynomials are degree 2 or less, my resulting polynomial is still degree 2 or less, so it's still in P2. Next, my scalar multiplication, when I multiply scalar A times B, scalar alpha times B, then I have my alpha and my polynomial of degree 2 or less, and you can see that the result is still a polynomial of degree 2 or less. So the scalar multiplication is closed. Next, I need to show properties of addition. The first one is commutative. So when I add two vectors, I can commute them. So when I have a plus b, here's my vector a, vector b, I add them together according to my definition. But now I have a1 and b1 as well as they're both just real numbers. So I can distribute my x across those, as well as this a1 and a2, they're both real numbers. So I can distribute my x squared. And then I can regroup things so that I have b plus a. For a2, associative, so I have a plus b plus c. So I have my polynomial a here and my polynomial b plus c, which I've added together here. And then when I add a in, I get this polynomial just by polynomial addition. And then I can rearrange terms algebraically until I get a plus b added together and then c added at the end. Last, I need to, not last, but I also need to show additive identity. So my 0 vector is just the 0 polynomial, which I can represent either with a 0, or if I want to be really explicit, it's 0 plus 0x plus 0x squared. So if I want to add a to my 0 polynomial, then I have a plus a1x plus a2x squared plus 0 plus 0x plus 0x squared, which is just equal to a. Then I need to find, for every vector, I need to find its additive inverse. So if I have a vector a, then its inverse is going to be negative a naught minus a1x minus a2x squared. And so you can see when I add them together, I get my additive identity. Next, I need to show my properties of scalar multiplication. So if I have this, a scalar a times b times our vector, that's equal to ab times the vector. So I have a scalar a times a scalar b times a polynomial. So when I multiply, just by using scalar multiplication of polynomials, I get this beta plus a naught plus beta a1x plus beta a2x squared. And then by multiplying by my next scalar alpha, I get this expression here, my alpha beta a naught plus alpha beta a1x plus alpha beta ax squared, or a2x squared. And then I can pull out my alpha and beta because these are just real numbers now. And I get alpha beta times my polynomial a. M2, I'm on M2. So I can add my two vectors multiplied by a scalar. So I have that, I added my two vectors multiplied by a scalar, and then I can rearrange things algebraically until I get alpha a plus alpha b. And next, I need to show this distributive property where I add two scalars and multiply by my vectors. So my scalar is alpha plus beta times a. So then I expanded out my a for my polynomial. And then I can multiply my alpha beta by each term. And then I can use my distributive law because now I just have real numbers. So I distribute, and then I can rearrange my terms, so eventually I get alpha a plus beta b. I mean, I'm pretty close here. And then last, my scalar 1 times any vector is equal to v. So my 1 vector is equal to the polynomial 1 plus 0x plus 0x squared times my vector a, my polynomial. So that's just going to give me back my original polynomial. So again, I've shown all 10 properties hold, which means that P2 is a vector space. I do have a lot to say about vectors, but I'm going to save some of the other comments and kind of analogies for another video because this is already getting quite long. But we do need to finish with talking about subspaces. So if V and W are real vector spaces, and if W is a non-empty subset of V, then W is called a subspace of V. So if W is a subset of V and they're both spaces, then W is a subspace of V. Now we have this theorem. If W is a subset, not a subspace, but a subset of a vector space V, so we have part of, some of the vectors are in W now, then W is a subspace of V if and only if these three properties hold. 1, the 0 vector of V is in W. 2, addition is closed, so U plus V has to still be in W. And scalar multiplication is closed. In other words, a scalar A times a vector V is still in W. And the reason why you don't have to prove all of these properties is because presumably, because it's a subspace of a vector space V, the properties of addition will still hold since it since it holds for all of V and W is a subset, again, these properties of addition should hold. These properties of scalar multiplication should hold. It's the closures that you need to worry about, and also the existence of the zero vector, the additive identity. So our first example, let W be the subspace of R3, be defined by W is equal to vectors x such that x is equal to x1, x2, x3, where x1 is equal to x2 minus x3, and x2 and x3 are just real numbers. So we want to verify it is a subspace. By our theorem, we have these three things to verify. First, we need to show that the zero vector is in W. In other words, that the 0, 0, 0, that's our zero vector of R3, that it does qualify to be in W, which it does because we just need x1 equal to x2 minus x3. And if we, for the 0, 0, 0, this is definitely satisfied. So the zero vector is in W. Second, we need to show that addition is closed. So here we have two elements in W. So we have A1, A2, A3, where A1 is equal to A2 minus A3. And we have B1, B2, B3, where B1 is equal to B2 minus B3. So when we add A1 and B1, so remember A1 is equal to A2 minus A3, and we add that to B1, which is equal to B2 minus B3, and we have A2 plus B2, A3 plus B3. But on the top, we have our A2 minus A3 plus B2 minus B3. And to be in W, we need x1 to equal to x2 minus x3. So this is x1, our top coordinate. I can kind of rearrange these because these are just real numbers. I can group my A2 and my B2 together and then subtract my A3 and B3 together. And I guess this should be a plus. So then, oh, that one, not that one. So then what I have then is this is my A2 plus B2, and over here this is my A3 plus B3. So I have exactly the correct form that I wanted. So addition is closed. If we look at alpha A and look at the form of this, so our top coordinate is going to be alpha x2 minus x3, because remember x1 here is equal to x2 minus x3. So when we multiply by alpha, we can distribute our alpha into our and multiply both, and then we essentially just get alpha times x2 minus x3. So that's this here is exactly these two terms. So our first term is equal to our second coordinate minus our third coordinate. So this means that W is closed under scalar multiplication. It fits these three conditions, and therefore W is a subspace of R3. And what would really help is to look at something that is not a subspace, that fails some of these conditions. So we're going to take this example where W is a subset of R3. In other words, we're going to look at the vectors where the z-coordinate is equal to 1. Again, that is a subset of R3. So we want to show it is not a subspace. First, let's look at the zero vector, which is equal to 0, 0, 0 for R3. And this is not in W because the z-coordinate is equal to 0 and not 1. So this is enough. The lack of zero vector is enough to show that W is not a subspace of R3. But we're still going to look at addition as closed. So let's take a vector with 1 in the z-coordinate and another vector with 1 in the z-coordinate. And you see when we add, we get a 2 in the z-coordinate. So this addition is not closed in W because this is not in W, right? Because its z-coordinate is equal to 2, not 1. So addition not being closed is also enough to show that W is not a subspace. And last, let's look at scalar multiplication. So if we take alpha times x1, x2, and 1, we get alpha x1, alpha x2, and then alpha, which, unless alpha is equal to 1, in general, though, alpha is any scalar, so scalar multiplication is not closed. And this one condition, S3, this is enough also to show that W is not a subspace. So essentially, it failed all three conditions, but showing any one of those three conditions failing is enough to show that W is not a subspace. And we'll do another where it actually is a subspace. So we're going to look at 2 by 2 matrices. And W is going to be our subspace that has zeros on this diagonal here. And then it just has regular entries, A1, 2, and A2, 1. So we're going to verify this is a subspace. Now 3 conditions to show. First, we have to show the 0 vector is in W. So 0, 0, 0, 0 definitely satisfies this condition where A is on this diagonal. We just happen to have A12 and A21 also equal to 0. But this is satisfied. Second, addition is closed. So if I take a matrix with zeros on the diagonal, add it with another matrix with zeros on the diagonal, I still get a matrix with zeros on the diagonal and a 2 by 2 matrix at that. So this is also in W. Addition is closed. And scalar multiplication, that's my, not an X, but it's supposed to be like a multiplication. I got lazy and didn't want to write out multiplication. So scalar multiplication is closed. So if I have a scalar alpha times a matrix with zeros on the diagonal, I still get a matrix with zeros on the diagonal, a 2 by 2 matrix. And so that's also in W. So my 3 conditions are satisfied, and therefore W is a subspace of V. Ooh, a new kind of vector space. We're going to let W be a subset of the space of continuous functions on AB. So W is equal to f of x in the space of continuous functions such that f of a is equal to f of b. We want to verify W is a subspace. So first we need to show that the 0 vector is in W. So the 0 vector is the vector or the function that you can add to any other function and get back that function. So that's f of x is equal to 0. So f of a is equal to f of b is equal to 0 for f of x equals 0 for the 0 vector. Therefore, this condition is held and the 0 is in W. Second, addition is closed. So if I have 2 functions, f of x and g of x, such that they are in W, in other words, f of a is equal to f of b and g of a is equal to g of b, then when I add them together, I'm going to let h of x equals f of x plus g of x, and I get h of a is equal to f of a plus g of a. Now, since f of a is equal to f of b, I can substitute f of b, and since g of a is equal to g of b, I can substitute g of b, and then I get f of b plus g of b, which is equal to h of b. So here I have shown that h of a is equal to h of b, so addition is closed. Scalar multiplication is closed, so alpha times f of x is equal to alpha f of a, and because f of a is equal to f of b is equal to alpha f of b, so then I have, since, again, alpha equals b, then I have alpha f of x is equal to alpha f of b. I should have said alpha f of a is equal to alpha of f of b. So anyway, scalar multiplication is closed and W is a subspace. So we have talked about vector spaces. We've done 3 examples of vector spaces. Then we talked about subspaces and we did some examples of subspaces. For review, I have these 2 problems for you to try. So pause the video, give them a try, and on the next slide, I'll have solutions. This is the solution for the first problem, and this is the solution for the second problem. And that's it for this video. As I said, I do have a lot more to say about vector spaces, but that will be in my next video. It won't have a lot of calculations, but more concepts. Okay, thank you for watching.